I did this series on antimatter. That reminds me, I've been meaning to take. I made that series, and then I was like, oh, I'm gonna clip all those together and make one log antimatter video. Like that was always the intention, but I thought that like I would remember to do that. I'm gonna do that. I'm gonna remember to do that right after I film this. That's what's gonna happen today. I wanted to do a video on antimatter, and I wrote down a list of things I would want to talk about, and I did the physicist thing where I was like, I'm going to talk about antimatter engines. I don't need to look that up. I get how it would work. It's probably a simple idea. It's fine. And then I went to film the video, and I was like, I should probably Google that just to make sure. I don't want to make a fool of myself on the internet. And I found this article by Googling antimatter engine, and it was on a website called HowStuffWorks.com, which perfect because I want to know how an antimatter engine will work. And it was called How an Antimatter Spacecraft Will Work. Not how it could work or if it would work, but how it will work. And that's what I've been doing for the last 2 weeks. So let me just take you through the highlights of this article called How Antimatter Spacecraft Will Work on HowStuffWorks.com. And it's written by Kevin Bonsor and Yara Simone, and it's from August of 2023, which, yay, what a recent article. The most recent updated information on antimatter engines. This is so perfect. And let me just walk you through it. So they start by talking about the warp drive on Star Trek, which is not related to the antimatter engine on Star Trek, but I'll give it a pass, like fine, whatever. And then they just keep saying antimatter will make you go fast. It'll make you go fast, and okay, I'm sure they'll explain that when they talk about the engine. That's perfect. They talk about what is antimatter, and they say antimatter is the opposite of normal matter, and I'm like, oh, so this is an article for children. I mean, fine. It'll still probably explain the basic concepts. That's fine. It's not going to have research in it, but that's fine. And then it starts talking about Paul Dirac and negative mass, and that's incorrect, okay? And then it talks about the types of antiparticles we've made on Earth, the positrons, the antiprotons, the anti-hydrogen atoms, and it talks a lot about CERN, which has a particle accelerator which can make antimatter. It talks about when antimatter comes in contact with normal matter, it explodes in a big explosion, and that explosion makes you go fast. It's a big explosion, bigger than any scientist has ever seen. Big explosion, you go fast. And that's kind of the whole article. And this was so confusing because I don't understand. Like, it's in English and I can read all the words, but when you put the sentences together, they don't mean anything. This article is called How an Antimatter Spacecraft Will Work, and yet it doesn't do what it says. It doesn't tell me that. It just says antimatter is the opposite of matter. It's made in CERN, and if you put it together with normal matter, it explodes. It uses words like pure radiation and superluminal, and talks about negative mass, and so I did the normal thing. I investigated it. That's a normal thing to do instead of just clicking back and finding another article, right? If you scroll to the bottom of this article, there's a very interesting sentence which says, this article was updated in conjunction with AI technology, then fact-checked and edited by a HowStuffWorks editor. And I don't believe you. I don't believe a human being has ever read this article because it doesn't make any sense. If it was edited, how? In what way? Wouldn't the editor perhaps remove all the factual errors? So I did another normal thing, and I copied this article into a Word document, and it's about 1,500 words, which definitely seems like you had an AI language learning model, and you were like, please write me 1,500 words on how a antimatter spacecraft will work, and it did that. And then when you remove like the captions to the images and all that stuff, you have about 1,300 words, which I have highlighted into categories. Because I'm fun and stuff. Okay, so the first thing I did was highlight all the factual errors in green, and this is so surprising. Listen, I'm a little nitpicky here. Like, the Star Trek thing is wrong, but like, would you expect Kevin and Yara to have seen all of Star Trek and know the difference in the antimatter engine and the warp drive and actually what makes the Enterprise go fast? I don't know. And this video is not going to be about particle physics. I'm not going to go into why all these are factually incorrect, but let's just do one. So this article says that antimatter is exactly what you think it is, the opposite of normal matter, and that's fine. Like, that's a fine definition for children. Like, a proton is a certain mass, it has a certain charge, and it's made up of 3 quarks. And an antiproton is the same mass, the opposite charge, and it's made up of 3 antiquarks. So they're opposite, right? Same mass, opposite charge. That's fine. But then in the very next paragraph, they say these antiparticles are literally mirror images of normal matter. And there's a thing in physics called chirality, where it talks about like the handedness of things. Like, when you hold your left hand in a mirror, it looks like a right hand, right? They're mirror images of each other. Right. Your right hand is not an anti-left hand. It's still a hand, right? The handedness on a proton is its spin. Okay, so when you look in the mirror of a proton, you're seeing the opposite spin. Like, that's the handedness. It has nothing to do with the antiproton, which also has a spin and also has handedness. So this is just a very confusing, incorrect sentence, and it also goes against what you just said, which was that it's the opposite. And it's that kind of thing that makes me a little suspicious, because I think an AI would catch that. I know I shit on AI a lot, but if you watched that video closely, you would see me say these tools are useful. These tools, the ones that are trained well, produce good things. You just have to check the output for accuracy. You need an expert to check the results. You need an expert to check these results. And so I don't think this article was edited by an editor on HowStuffWorks.com, because there's so many glaring just errors. There's so many errors. The things I've highlighted in pink are just like kind of unrelated to the article at hand. This article says it's going to describe an antimatter engine, and what it actually does is talk about Star Trek, incorrectly label what antiparticles are, does a bunch of definitions about this is when this particle was discovered. It talks about what CERN does, and then it just throws a bunch of like, it's as much energy as a light bulb. It's as much energy as 1,000 suns and stuff. But they also just kind of throw things in there. Like, why not discuss the origin of gamma rays? It talks about, in 1978, people finding antiparticles in the universe. And that's not related. Like, are we going to drive to the center of the galaxy and pick up the antimatter and then we wouldn't have to make it? It doesn't make any sense. And again, AI is better than this, which makes me flip-flop. And my new working theory is that the editor read the AI article and found it dry, and so started inserting like a bunch of, it's just like this, it's just like this, which is somehow worse. Like, is the editor not a scientific journalist? Is it just a random person that's just like, ooh, you know what we could do? Add random sentences. And this theory is bolstered by my next highlighting, which is just for every time they repeat something. The amount of times they say antimatter will make you go fast without explaining how it will make you go fast, because that would be explaining how the engine works. And I'm worried that that's too much to ask from an article titled, How Will an Antimatter Spacecraft Work? You can't explain how it will work. There's not enough time in the 1,500 words. Instead, we'll say it makes you go fast 7 different ways. I'll read you one. It's like the difference between driving an Indy race car and a 1971 Ford Pinto. In the Pinto, you'll eventually get to the finish line, but it'll take 10 times longer than in the Indy car. Why is an article from 2023 referencing a 50-year-old car? Is that a real car? Why would you name your car after a bean? Is that a thing made up by the AI, or does that exist? Why would you add that in? What does that add? You're limited to 1,500 words. That's about the length of an Instagram caption. And you think that sentence merits erasing all the information on, I don't know, answering the titular question, this is how the antimatter spacecraft will work? In orange are the definitions, which is a thing I think you limit with your AI. You just say, like, please write an article of this length, only 20% definitions. That's the same thing you tell like ghostwriters in books, right? And so that's what I think this is. Like, let's define an antiproton and when it was discovered, and then we'll do an antihydrogen, and we'll just define everything in the world instead of using simple language, because this is an article for children, right? Right? And then in yellow is just how an antimatter spacecraft will work, except not really. It just lists 3 things you'll have. Like, oh, you'll have to have a magnetic field to hold in your fuel, because your antimatter can't touch matter or it explodes. And then you'll have to have a feed system to take the antimatter from the little trap to the engine. And then you'll have to have a magnetic rocket nozzle to push the explosion out. And, you know, I'd be interested in why you need a magnetic trap for your antimatter, or how the feed system works, or why you need a magnetic nozzle. Why? Wouldn't that be an interesting thing to discuss in this article? Wouldn't that be fun? Or you can just talk about how many grams we'll need to go to Mars. You don't need to know how the engine works. You don't need to know any of that. It's fine. Just, it's gonna make you go fast. And the explosion's a lot of energy that makes you go fast. That's the article. I've highlighted in red the funniest bit of this article, because the whole article is like, here's how it will work. That's the title, how it will work. It says, like, let's peer into the future a couple of decades and see what it'll be like when we have a working, fully fledged antimatter engine. And then it just says, all of the antiprotons produced at CERN in 1 year would be enough to light a 100-watt electric light bulb for 3 seconds. So it's not gonna work, is it? Did you address this in the article? You didn't. How will it work? If it'll only power a light bulb for 3 seconds, how is it working? How will the engine work? That's the title of the article. How will it work? So this is bad. It's a bad article. It's bad writing. And all the references are like 20 years old. Like, are you really referencing science missions from 2002? That's 20 years ago. What is this? Are they using a 20-year-old AI to write this? Is that why it's so bad and the writing is so bad? Who is this for? And if you go to the HowStuffWorks website, it's 100%, I think, for children, because when you click on it, there's like a little cite this article button and it pops up in MLA format and you can just copy and paste it into your Word document. But like, children can read, and this article is barely intelligible. So wouldn't they notice that it's really bad? There's a section on this website where you can report errors, and I kind of just want to send the whole article and be like, it's an error that you posted this. Was it an accident? Like, it's been up since August 29th. Has anyone noticed? Like, have they received a bunch of emails that are like, what is this? What is this garbage article that's on your page? It doesn't make any sense. How exactly will the antimatter spacecraft work? I'm still curious. The article didn't answer that question. I picture an 8th grader who's waited till like the last second to write his little homework assignment on antimatter spacecrafts, and he gets this article and he's like, I guess I just don't understand it, and he just copies and pastes it into his assignment. And then his teacher is like, oh my god, Billy, this doesn't make any sense. Do you even understand what you're writing? Like, if Billy turned in this article, his teacher would call his parents and be like, I'm so concerned that Billy's not at an 8th grade reading level yet. This is incomprehensible. We need to like get him a special tutor outside of school hours. We might have to hold him back because this article doesn't make any sense. What he's written is barely sentences. We've been failing Billy. It just makes me kind of sad because I used to go to this website like 20 years ago. This website was started by a physics professor, teacher, who just like, I'd like to write fascinating articles on how stuff works. And I loved that shit when I was like 10 years old. In the year 2000, on the early internet, I would be like, I do wonder how a microwave works, because I was in Kentucky and that's how I talked. And I would get on there and I would just read for days and days and days. Let me show you, because the Wayback Machine works. Okay, so I'm on the Wayback Machine. And just look at the old internet. Look at the, just the font and the colors, and like everything was set up like this, like the same way you set up like a file system. And the way advertisements used to work was like every time you loaded a page, it would show you the ads. So every article would be split into like 17 pages and you would just have to click the next page. Oh my gosh. This brings me back to being 10 years old, and just like, I miss the old internet sometimes. Okay, so this is what it looked like in like 2001. And then, okay, so now we're in 2007. HowStuffWorks, now it has videos. It still has the Google search. They've decided to go with blue, which is also a thing. I feel like web pages used to be like sepia and like yellow background and just like really old computer style, and then they all shifted to blue. But I thought that it was purchased by the Discovery Channel, so we're gonna, oh my gosh, they have videos now. 2007 is when they get videos now. Okay, here we go. Somewhere before 2010, HowStuffWorks.com was purchased by the Discovery Channel, and it was a Discovery company. And they still have like, they had show tie-ins, they had like podcast tie-ins and stuff. And isn't how this stuff goes on the internet? Like, someone makes like their dream little website and it gets popular and they sell it to a giant company, which, like, good for that guy. Congratulations. That's perfect. But if we move forward even further, you can just see that this website keeps getting more populated with ads. Just even now, like, if you compare the modern version of this article to the one with ad blocker turned off, it's just like pop-ups and autoplay videos everywhere. And it's just like, how is anyone even supposed to read this garbage article that's barely English in the first place with all these ads? But that's what's happening here. You see lots of ads, those weird ads. Oh, podcasts. Okay, so it's 2013. That's early for podcasts. I don't think I've ever listened to any of these podcasts. It's fine. I'm sure they're fine. And then we can jump forward to 2021, and this no longer is a Discovery thing. So Discovery, I don't know, as a company, did it shut down? Did it get sold? But now we're here, and so I think astute viewers will have realized that I wasn't doing the Wayback Machine on HowStuffWorks.com. I was doing the Wayback Machine on this specific article. This specific article that says it was written in August 29th of 2023 was on HowStuffWorks.com in 2001. This is not a new article. This is a 20-year-old article. Which means it was written by a person. I owe a big apology to Kevin. I'm sorry I said your article was so bad that an AI couldn't have even written it, but I was right. So this is not Kevin's fault, right? It's a really bad article, and he wrote it, and it's really, really bad. But I went to his university's newspaper's archive and I found the previous articles that Kevin had written as a journalism major, and they're totally fine. They're totally written in English. They have a point and a flow, and one can read them and understand what's happening. So this is not Kevin's fault. Kevin is not a scientific journalist, or he wasn't at this point, literally 20 years ago. Has no one read this article in 20 years? Like, I assume Kevin, college grad, was applied to a job that was like, write exactly 1,500 words. It can't be more than 20% definitions once a week, and we'll give you whatever a salary was in 2000, like $10. I don't know. And he was probably given a topic like antimatter engine, and he's not a scientist, so he just wrote what he thought would be okay for that, and he sent it to presumably his editor, and his editor didn't read it, and he was just like, slap it up, it's fine, it's the year 2000, surely this won't exist, in 20 years, whatever. And like, I said I liked this website 20 years ago, and this whole time I was like, well, this is how it is now. It must have been good when I liked it as a 10-year-old, and it turns out no, it wasn't. Did anybody read the articles that the authors they like outsourced, the freelancers, were writing? Has that just sat on this website for 20 years? The text of this article has not changed in 20 years, except for adding the AI component. What did the AI do? It's the same article. It didn't even update the references. It didn't even update with recent space missions or recent like enhancements in how we make antiparticles. What did the AI do? And what about Yara, our second author? She was added in this year. She was added with the update in August 2023, but I know she didn't write anything because the text is the same as it was 20 years ago. And I don't think she read it, because if she read it, surely she wouldn't have put her name on it, or she would have rewritten it, because it's really, really bad. So I owe Kevin an apology, because this is a shitty article. It's really, really bad. It doesn't belong on the internet, but it's also written by someone who is not trained to do this, and someone should have guided him. Like, when he got this job, his editor should have been like, whoa, this is not good enough to be put on the internet, and they should have coached him. They should have worked with him to get a better article. Instead, Kevin has hundreds of articles on this site. When I searched his name on the HowStuffWorks website, I saw so many articles, and they were all plus and. So they must have had a recent rebrand where they had all these articles updated, even though, as I said, this one has no updates at all. And they just added a second author to make it seem like someone had worked on this stuff recently, because this is a dying website, right? No one is going to this website. The Discovery Channel probably sold it off, and whoever bought it is just running off the clicks that they get. They're not going to add anything. It's just like, we're going to leave this corpse here that people will click on because they remember how stuff works as like a thing, and they're going to click on any article and they're going to be like, oh, this is just garbage, and they're going to feel bad, and they're going to backspace and find an actual article on the topic they were interested in searching. If we go back to that 8th grader, these articles do read like an 8th grader was tasked with a topic that they are not interested in, and they waited till the last minute, and they are just writing something they know doesn't make any sense in like hopes of partial credit. Like, there's this thing that I noticed that people do, I call it like science talk, where they don't know the answer to a question, but it will work better if I give you an example. If you watched my video on dark matter, I listed a bunch of evidence for dark matter. Now, if I gave you a quiz right now and I said, give me an example of evidence for dark matter, what would you say? If you saw that video. If you didn't see the video, you probably don't know, it's fine. What would you say? So if this was a quiz, a 10 out of 10 answer would be like, one example of evidence for dark matter is the rotation curves of galaxies. Stars at the outskirts of galaxies rotate much faster than we would expect based on the amount of matter we can see, so there must be some matter we can't see. They call that dark matter. Perfect. 10 out of 10 answer. What if you just wrote down like rotation curves? I mean, fine. I like a full sentence. I like when you demonstrate that you know what you mean by rotation curves, but like 5 out of 10. Okay. In real college courses, you get like this science speak answer, which would be something like, in the 20th century, scientists observed something interesting. The phenomena heretofore informed as dark matter could not be observed with normal methods. As a result, new innovative techniques need to be developed to observe this heretofore called dark matter. Scientists have nomenclatured this as dark matter because it is dark to the eyes, unlike light, which is observable. And they would just write that down. And that is English. Those are words, but that sentence means nothing. 0 out of 10 points. I asked, list some evidence of dark matter, and they said, dark matter is a thing you can't see. 0 points. These articles read like that. Just like someone's like, yeah, I can do time travel. Doop, 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 doop. And I feel bad. But also, they publish these. I don't want to be mean, but they're really bad. Why does this website exist? Why do these articles exist? Who is this for? So my new theory is that all the articles that have ever been on this website that weren't written by the original guy who was very passionate about this project are by recent grads that they can pay very little to produce whatever, and they just put it on the website and no one ever reads it again. This article has sat in this same state for 20 years and no one has ever read it. No one has ever read it, because how could you read it and not send an email immediately to the website and be like, hey, there's many factual errors. It doesn't answer the question it poses in the title. This is a very bad article. So I just have to imagine that no one's ever read it. And I don't blame the authors of these articles, because writing is very hard. I am a bad writer. In fact, I would like to compare this article to an article I wrote in the year 2011 when I was also 20 years old and will live on the internet forever, because the professor in the course put it on the internet and there it is with my name on it, and that sucks. Okay, here's the article. It's called Scientific Literacy, Why It Matters, by Angela Collier, April 21st, 2011. Your girl is nothing if she's not on brand. That's right. I have been talking about science education and scientific literacy and scientific communication for like a decade. Yep, that's my personality. Sorry. I will link this garbage article below if you want to read it and make fun of me. It's fine. But it's the same thing. It's the same kind of, oh, this is how a scientist would write. Here's my point. Aren't my jokes? It's terrible. It's a terrible article. This needs an editor. Just like this entire website needs an editor. This is so bad. I talk about those power balance bands, which is like a vintage scam, but it was like this plastic bracelet and they were like, your frequency, it balances you. And it was just like plastic. And these athletes would wear them. Bill Clinton wore one, and it's just like, it's a plastic bracelet. Obviously it does nothing. And the whole point was like, this is why scientific literacy is important, because you can get scammed and people will steal your money by telling you bullshit. And this article is very bad. There's one line I regret specifically. I'll read it to you. It's pretty hard to believe that in 2010, a former porn star convinced a little under 8% of Americans that vaccines cause autism. I regret the choice of the word porn star, because the problem is, of course, not that Jenny McCarthy was a porn star. I don't care about that. Be a porn star. I support sex workers. It's totally fine. The fact is that what I was trying to say is that you shouldn't take medical advice from people who aren't doctors. And that point still stands. I can't believe it's 10 years later and Jenny McCarthy still walks around. I can't believe she shows her face. Like, she literally is responsible for the deaths of children from preventable illnesses, and she just gets to walk around and go to restaurants, and I'm still salty about it, and I don't like it. This is why scientific literacy is important. But this is a bad article. It's particularly bad. My solution was like, just teach kids science, which is like so lazy. It's such a bad solution. This is also a bad article. I'm sorry, Kevin. We all wrote bad articles 10 to 20 years ago. I'm sorry that yours got updated. And I'm sorry that mine is deep, deep, deep in search results, whereas yours is always on the first page of Google, and it has been for 20 years. If you Google antimatter engine, antimatter spacecraft, that sucks. That article does not explain how an antimatter spacecraft will work, and yet it is always on the first 3-ish Google results. It has been for 20 years. The article says nothing. It's a garbage article, and yet it's the first thing people click on. It's like this whole website, instead of paying writers to write the article, which is literally the product they're selling, they just paid like SEO engineers to make sure that it's always on the top. It's always on the top. It doesn't matter that it says garbage. You click on it. And that's what makes me mad, because that means this website is a scam, and they have scammed me for the last time. And I'm telling you now, never click on this website. It's always a scam. They stole from me. They stole my time. I just wanted to learn how antimatter engines work. I clicked on an article titled, "How Will Antimatter Spacecraft Work? How will they work?" And it didn't tell me. I wasted seconds of my life scrolling through incorrect Star Trek information to be met with incorrect physics information, and it didn't tell me how the engine worked. Scam. It's a scam. And this is a dying website. Like I said, they are just living off the corpse of the SEO clicks, where you click on it, you read an article for 4 seconds, and you're like, oh, God damn it, and you click back to find an actual good article. Are we just gonna let these SEO corpses ruin the internet? Are we just gonna let these exist at the top of our Google results? Are we gonna let this garbage ruin the internet? I guess. That's the thing though, right? No one's gonna be like, well, take the website down because it lied to you. And I don't think we should take the website down because it lied to us either, but it just sucks. It just sucks that like they hire the smartest minds of our generation. You might think smart people do physics and medical science and doctoring, but no. The smartest minds of our generation are doing SEO and figuring out how to put ads on the ads on the ads so that you can never see anything without being penetrated by what your company wants you to see. Do we just let them do that? Would the solution be to just have government grants where we take all the SEO engineers and just give them money to follow their passions? Why don't they make better video games? They could just make video games. That would be great. Why is it this? Why are they pushing this onto us? This is garbage. But I can see how someone would say it doesn't matter, because like, we're adults. We click on it. We read it for 10 seconds, we realize it's garbage, and we angrily click the back button, but like they just stole our time, right? It's not that big of a problem, right? Let's read how 2011 Angela Collier defined scientific literacy. Scientific literacy means that a person can ask, find, or determine answers to questions derived from curiosity about everyday experiences. That's such a bad sentence. It means that a person has the ability to describe, explain, and predict natural phenomena. Keep with the commas, Angela. You need an editor. Scientific literacy entails being able to read with understanding articles about science in the popular press and to engage in social conversation about the validity of the conclusions. Scientific literacy implies that a person can identify scientific issues underlying national and local decisions and express positions that are scientifically and technologically informed. A literate citizen should be able to evaluate the quality of scientific information on the basis of its source and the methods used to generate it. Scientific literacy also implies the capacity to pose and evaluate arguments based on evidence and apply conclusions from such arguments appropriately. And because of the way I understood writing in 2011, I have this little link to the National Science Education Standards, and I bet I just copied that information and then thesaurized it, and that's what I just read to you. But you get it, right? Scientific literacy. If you Google, "Are Americans scientifically literate?" you will see a research study from the Pew Foundation in 2019, and they're like, "Oh my God, you guys, Americans are so scientifically literate. Yay!" But I disagree with that. I don't disagree with their study. I disagree with the conclusions. So they did a big, huge survey of a bunch of people, and they gave them all multiple choice questions like, explain human evolution, and they had to pick A, B, C, or D, and like, explain how vaccines work, A, B, C, or D. And people did really well on those. But I don't think multiple choice tests can determine how scientifically literate someone is. It determines how good they are at answering multiple choice tests. There was a great quote in the NPR article about this Pew Research study where it was like, if you ask Americans how evolution works, you're not really asking them anything about science. You're just asking them what religion they are. Scientific literacy is a very hard thing to measure and study. I would say that I like my definition from the article, but it could use some edits. But I would expect a scientifically literate person, someone who knows nothing about particle physics, someone who knows nothing about Star Trek or like engines, should be able to read this article, how an antimatter spacecraft will work, and they should be able to realize, not knowing any of the science is wrong in the article, they should realize that that's a bad article. Because they should be like, okay, this article says antimatter makes you go fast, and it says the explosions are big, but it's missing this middle piece. This article is a bad science article because it doesn't explain how the engine works. And a scientifically literate person knowing nothing about physics should read that article and come to that conclusion. This happens to me a lot with biology articles. I've been trying to teach myself molecular biology, and it's very difficult for me, and I now understand why all those pre-med students were always carrying around like giant flashcard decks. But sometimes I'll click on an article and I'll be reading it, and because it's a topic I'm not informed about, I will be like, wait, this is confusing. And then this thing happens where I'm like, oh no, I'm just an idiot. I can't understand this article. But sometimes I'm not an idiot. The article is garbage, written by AI and checked from 20-year-old information. And because I'm scientifically literate, or at least I consider myself scientifically literate, I don't know how you measure it. If the government gave me 18 months and $700,000, I would develop a test for it. So hit me up, NSF. But I would consider myself scientifically literate. So when I'm reading those medical articles that are bad, it takes me a couple seconds to be like, oh wait, this doesn't make sense. Like, they're just defining things a bunch of different times, or they're not explaining the mechanism, so I can't follow it. And you have to be scientifically literate to be like, okay, I don't understand, but it's not because I don't understand, it's because the information is being presented poorly. And I do not think most Americans have that skill. I'm going to give you an anecdote because, like I said, I don't think this topic has been studied in the way I would consider a successful study of scientific literacy. I have taught college courses in multiple different states at multiple different universities. And every time I teach an entry-level college course, the first thing I do on the first day is I give a homework assignment that's like 4 algebra questions, because a lot of people are just like shocked and surprised that something like astronomy or biology 100 is going to have math in it. Math is really important in science. It's always going to be there, guys. But the bottom part, I would put on like a little simple line plot like this. And I would ask these college students, which means, they graduated with a high school diploma. These people have applied and been accepted into universities, and they've signed up for a science course, which means they think they'll be able to do well in this science course. I would ask them to look at this line plot. So I would ask 3 things. And the first is like, what does this plot say? And it would say, peak traffic times are between 6 and 9 a.m. and 4 and 6 p.m. or something like that. And then I would say, if it's 10 a.m., how many cars are on the road? And that would require them to like draw a little line up and draw a little line over and get the data point. And then I would ask like an analysis question, like, why do you think there are 2 peaks on this graph? And there are hundreds of right answers to that question, but you would expect someone to say like, the peaks are associated with people going to work and coming home from work. That's when most people are on the road. That's why the peaks are highest right there. Yay, 10 out of 10 on the graph quiz. But the thing is, I would give this to a class of like 110 students, and like 30% of them would not get those questions right. Like 30% of the college freshmen could not read a graph that looks like this, and they're in a science class. And I don't think it means that 30% of people are stupid or those 30% of people could never be scientists. It's just that they're not scientifically literate. Maybe they learned how to read a graph one time in 7th grade and they haven't thought about it since and they don't know how to do it. People would come to like my office hours and they would say, you can't give us a homework like this. You didn't even go over how to do this. And I would be like, thanks so much for coming in. Let's learn how to read graphs, an important necessary skill for every adult human to have, you know, in case there's a global pandemic or something and people have to read graphs. And so when you think about these articles and people are like, well, the 8th graders will figure it out. It's good for them to learn which articles are good and which articles are bad. I'm not thinking about the 8th graders. I'm thinking about like just a normal human person who's like, I'd like to write a sci-fi story. I'm going to look up how an antimatter engine works to build the background to my story. And they click on this article and they can't recognize that it's a bad article and that it's garbage writing and it doesn't make any sense. I'm so sorry, Kevin. And they just think, I must be too stupid to get this. I don't understand how these antimatter engines work. And I just read an article called How an Antimatter Spacecraft Will Work. And I don't understand it. I must be stupid. And that sucks because they're not stupid. They're just reading a garbage article that doesn't explain it. And that's the problem with this. These whole things are a scam and I don't like it. And it's making everything bad. An antimatter engine is a pretty simple thing to explain. And I think you could explain it on an 8th grade level. And why is this the first link? Why is this the first thing that people search? Because it's a tragedy that someone would just sit down and be like, I'm going to learn something right now. And then they click on this and they don't understand and they feel embarrassed. That sucks. I hate it. It's a scam. Nobody ever click on this website again. So this is the antimatter video. Antimatter. Antimatter. It's fine. The first thing I want to say is that, yeah, it's a terrible name. Antimatter as like a word evokes like this, but antimatter and matter are the same thing. Like they're made the same way. They interact with each other the same way. They interact with the forces the same way. If you took every piece of matter in the galaxy and replaced it with it like its antimatter counterpart, you wouldn't even notice. It would be identical. I mean, electricity would go backwards, but that's just like a naming convention. I think that leads to confusion. So today we'll be talking about antimatter, and I hope to go through some more of these confusing things about it. So, you know the standard model of a very successful theory of physics? You have all these particles, and there are so many, and they have so many names like fermions and bosons and leptons and mesons and hadrons, and I'm not going to get into all that, but you should know that every single one of these particles has an antimatter counterpart that you could put over here. I want to specifically talk about protons and antiprotons, electrons and anti-electrons, which are sometimes called positrons, but I think that's confusing when that's the only one that has a name that's not just anti, whatever, and photons. And the antiparticle for photons is a photon. If you look at the electron and the anti-electron, an electron is just a subatomic particle. It has a certain mass and a certain spin and all of these quantum numbers, and it has a negative charge. An anti-electron has the same mass, it can have the same type of spin, and it has a positive charge. A proton, though, is a composite particle, right? Protons are made up of valence quarks, a sea of quarks, and gluons. So if you were to draw a schematic of a proton where you include the composite particles, you would see 2 up quarks and a down quark like this. And you might think, oh, an antiproton will be 2 downs and an up. But no. No. An antiproton, if you draw it with its composite particles, is 2 anti-ups and an anti-down. Yep, there are anti-quarks. We're not going to get into QCD, but quarks have colors and you have to conserve color just like you have to conserve charge. And so you see that these are red and green and stuff. The anti-quarks are not red and green. They're anti-red and anti-green. Everything has an anti. It's fine. That's what's happening. A photon is its own antiparticle. Great. Now I would like to talk about how antimatter was discovered theoretically within the standard model, but I am not going to do quantum mechanics again because I did that a few videos ago and I told you I will do the easiest problem there is, and it took me like 45 minutes and I didn't even finish it. So instead, I'm going to do the physics thing where I kind of illustrate for you how this happened. This is the work of Paul Dirac, a very famous physicist who is responsible for the discovery of antimatter. So we are going to do a kinematics problem, a very simple physics problem, in order to illustrate why antimatter exists and why it has to exist according to quantum mechanics in the standard model. It'll make sense, I promise. Okay, so imagine you're standing on a cliff and you throw a ball straight down over the side of the cliff, and the height from your hand to the ground is 30 meters. And I want you to figure out the time it takes, t, for that ball to strike the ground. So let's do it. I'm gonna draw the picture first. So here's you, and your arm is throwing a ball over a cliff, and this distance is 30 meters. I'm gonna call this position here y equals 0, which means the ground is located at y equals minus 30 meters, which means that initial velocity that you've thrown the ball down with is 8 meters per second is going to be negative 8 meters per second. And we also know the acceleration at this point is going to be minus 10 meters per second squared. And what we want to solve is what t is at this position. Okay, so let's do that. Let's write down our kinematic equation. Delta y equals v naught times t plus 1/2 a t squared. We can fill in minus 30 meters is equal to minus 8 meters per second t. 1/2 of 10 is 5, so that's minus 5 meters per second squared t squared. If we rearrange this, we just get the quadratic formula. So we have 0 is equal to minus 5 t squared minus 8t plus 30. So you can do the quadratic formula where t is equal to minus b plus or minus the square root b squared minus 4ac over 2a, where minus 5 is a, minus 8 is b, and c is 30. So if you plug this into a calculator, you get 2 answers, right? Because of that little plus or minus. So t is equal to minus 3.4 seconds, or t is equal to 1.8 seconds. Now, this shows us the limit of mathematical models in physics. We set up this problem according to like Newtonian dynamics, and it gives us 2 answers. But only one of those answers is right? You can't have negative 3.4 seconds. You threw a ball down. There is no way it took negative time to get there. Negative time doesn't exist. You can't go back in time, actually. So this is just wrong, wrong, wrong. So physicists call this boundary conditions. Like, we know that you started the problem at t equals 0. There's no way you went back in time. There's only one answer here. And the answer is 1.8 seconds. And yeah, you could work out what this answer means in the mathematical model, which is usually like, if that rock, instead of being thrown down, was on a parabolic path, if you go back 3.4 seconds, that's when it was at the same height. It doesn't matter because it's the wrong answer. This is the limit of mathematical models in physics. You have to really know the physics of your problem. You have to know the boundary conditions. You can't just do the math because you can't go back in time. There's no negative time. Okay, what does this have to do with antimatter? Imagine you're a quantum mechanic in the mid-1920s and you're wearing your overalls, you're covered in grease, you've had a really hard job at the shop all day doing this giant quantum mechanics problem. And you're almost done because you got 2 answers. One of those answers was something that looks like the mass of an electron, so an ME, going this way, and something else that looks like the mass of an electron going this way. But you know which way your magnetic field is going. You're going to impose the boundary conditions, and you're like, this particle, if it's going to travel in this direction, it has to have a charge of +1. And this particle, if it's going to travel in this direction, it's going to have a charge of a -1. And you say, haha, I know that electrons have a charge of -1, so this is our garbage answer. We can throw that away. That particle doesn't exist. The only particle that exists is the electron with a charge of -1. The only particle that exists with the mass of the electron and has a -1 charge. So it has to be this answer. I've done it, boundary conditions, I did physics. But then in 1928, well, Dirac's 1928 paper is wrong, and he talked to a bunch of people and corrected it. And so let's instead talk about his 1935 paper. In his 1935 paper, Dirac is like, guys, I don't think we can throw away this mass of the electron +1 charged particle. Who says this particle doesn't exist? Like, we can't just throw this away. How do you know it doesn't exist? So he says, you can't apply that boundary condition. Just because we don't know yet that that particle exists doesn't mean it doesn't exist. Why can't there be a particle with the same mass as the electron but the opposite charge of the electron? Maybe it's a positron, an anti-electron. Maybe that exists. They found the anti-electrons. And it turns out in their experiments, physicists had been seeing anti-electrons this whole time. What they would see is a track in like a cloud chamber or something. And from the radius of that track, you can calculate the mass of that particle. And from its direction, if you know the magnetic field, you can calculate its charge. So they had been seeing these anti-electrons all the time, but they were just assuming that, oh, a rogue electron was traveling through this experiment. And that has nothing to do with the interaction we wanted to look at, because that electron wasn't related to this. We can tell because it's not moving in the right way. And Dirac was like, guys, if you had even for a second thought about the statistical likelihood of just electrons just flowing through your boxes all the time going the wrong way, you would have realized that that was actually happening in the interaction. But anyway, that's antimatter. It has to exist because the standard model allows for it. It has to exist because quantum mechanics allows for it. And now we see those particles all the time. Okay, so my little kinematics example was supposed to show you that there are limits to mathematical models. You have to know the physics of your problem, you have to know the boundary conditions, and you can rule out erroneous answers. Like, just because the math works doesn't mean there's like physics applications of the math. I've actually done a video about that before. But sometimes you learn from your mathematical models that something could be there. And just because you haven't observed it yet doesn't mean it doesn't exist. And so that's what Dirac did. And he opened up the world of antiparticles. So I mentioned earlier that antiparticles are matter, just like matter is matter. We see them being made in cosmic ray collisions. Like, if you, I don't know, slam a bunch of energy together to make particles, and one of those particles you make is a proton, and it has the mass of a proton, and it has the charge of a proton, and it is a baryon like a proton, so it has a baryon number of +1. You also have to make the opposite of that in order to conserve charge. So you need to make a particle that has a charge -1. So that the total charge from that interaction is 0, right? You have the proton +1, you have the antiproton -1, together that's 0. And the antiproton has a baryon number of -1. So you have a +1 and a -1, you get 0. This pair production is how we expect antiparticles to be made, which kind of leads to a problem, right? If you think about the Big Bang, you go back in time, the universe is very, very small. And there's this giant explosion where everything is made all at once. according to the rules of quantum mechanics, you have to have conservation, so you have to have pair production, which means that for every proton you made in the Big Bang, you had to make an antiproton. And the thing about antimatter, which I haven't discussed, which you probably know, is the most important quality of antimatter, probably explains why it's called antimatter, evoking this, is that when you take a proton and an antiproton and you put them together, they annihilate. Now, annihilate is a very specific word in physics. People use it colloquially, like if you're playing a sport against a team and you beat them at the sport because you're really good at sports, you could say, like, we annihilated the other team. But that's not what it means in physics. In physics, it means very specifically that you have a collision where two things interact, and as a result of the collision, the two initial things are completely gone. They do not exist in the universe anymore. So a proton and an antiproton, when they collide, release a bunch of energy, they make a bunch of new subatomic particles, but the protons are gone. They do not come back. They are annihilated. That's what that means. So let me say about the start of the universe. Again, you have this big explosion of energy, right? We know from quantum mechanics rules that you make particles in matter-antimatter pairs, which means the Big Bang for every proton made an antiproton. But remember, the universe is still very, very small at this time. So you make all these protons and antiproton pairs, all of those particles should just immediately find an antiparticle because they're attracted due to the electromagnetic force, right? One's a positive charge, one's a negative charge. They're going to pull together and they're going to explode and annihilate immediately. So why are there any protons left at all? Why does matter still exist? How did that happen? This is an open problem in physics. I don't have an answer for you. I'm sorry, that's really disappointing, right? What happened probably was you had the Big Bang, a whole bunch of mass was made and a whole bunch of antimass was made, and the huge majority of the mass and the antimass slammed together and annihilated, but for some reason there was an asymmetry. For some reason there was a little bit of baryons left over, and all of those little bit of baryons formed all the galaxies and all the humans and all the things you know and touch and love. How? Why? What caused the asymmetry? Why? Why was it matter instead of antimatter? Does it matter? Does it matter that it was matter instead of antimatter? I don't think so. Just like the way we chose north being north, it doesn't really matter if all of a sudden we just decided to call that south. We could call all the matter antimatter and the antimatter matter, and it wouldn't make a difference. Would it? Why did the matter survive and the antimatter not survive? Open question. That's why we study antimatter. Well, I mean, that's one of the reasons why. The other reason is that it's cool. But if we learn about antimatter, we can learn about the start of our universe. We can learn about cosmology. Because what if we did make an anti-helium, two antiprotons, two antineutrons, and two anti-electrons, and it didn't behave like a helium? What if it was like a little bit different? That difference could help explain the symmetry breaking at the start of the universe. It could explain why matter won over antimatter. I was talking about the hydrogen atom the other day, and I was like, look at these energy levels. When you have an electron at this energy level, it wants to go back down, and it emits a photon of a very specific wavelength. And we can look at the spectra of those photons and know exactly what molecule we're looking at. Antihydrogen should have the exact same energy levels. So we could make an antihydrogen. And what if instead of having a binding energy of minus 13.6 eV, the antihydrogen had a binding energy of minus 13.41 EV? Wouldn't that be crazy? Then we could learn about cosmology. Finally, we would have answers, but it turns out like it behaves exactly the same, which is kind of what we predicted with quantum mechanics. But it would be cool if it didn't. What if you made an anti-carbon and the bonds were stronger or something, and you could be like, the aliens will be anti-carbon. So we know that most of the antimatter is gone. But antimatter is still made in normal everyday interactions the same way matter is still made in normal everyday interactions. One of the ways is through cosmic rays, just like interacting with the atmosphere. You can make it an electron and an anti-electron, and you can see those in your detectors. Another way is through radioactive decay. So things like potassium have these decay channels that will produce antimatter. Your body produces antimatter every day, all the time. The bananas on your counter, you've heard that bananas are radioactive, right? They have a bunch of potassium. One version of potassium is radioactive. It just emits a bunch of radiation, and some of that is antimatter. Neat. But physicists want to study antimatter, of course, to learn about cosmology and all that other stuff, also because it's cool. And because of that, we want to make antimatter. We want to make stuff that's bigger than like an anti-electron. And to do that, you need particle accelerators. Because in collisions, as I've been hinting at this whole time, you make pair production. If you make a proton, you have to make an antiproton. So what if you did that a bunch of times? You got a big old stockpile of antiprotons. And antiprotons are just antihydrogen ions. And then you got an antihydrogen ion gas, and you could study it. And wouldn't that be cool? So let's talk about CERN. I don't know why I always say CERN. There are so many different accelerators. Is CERN just the most famous one? All right. So I think I mentioned earlier that you can do pair production as a result of collisions. Like if you throw particles together, a bunch of crap comes out, and you can study that crap to learn about the world. So if you take two protons and you slam them together, one of the interactions results in pion production. And a pion is a subatomic particle that's like two quarks bound together. They're relatively low mass. The mass of the proton is 938 MeV, and a neutral pion has a mass of 135 MeV, while a charged pion has a mass of 140 MeV. So these are relatively low mass comparatively. So these reactions are like proton plus proton yields proton plus pion. So the way these guys work is you have like a stationary target. And if you want to do a proton-proton collision, your target has to be made of protons. Usually you just have like a stationary hydrogen gas. So like you don't care about electrons. Like electrons are garbage. They're so small. Your proton's huge. It's going to slam into another huge proton. The electrons don't even matter. So that's stationary. And if you want something to come out of this collision, you have to give energy to your proton beam that's going to slam into these stationary protons. So you might think like, okay, if proton plus proton yields proton plus pion, you just have to give that beam of protons 135 MeV. You give it enough energy to flip it into this other stationary proton, and they'll stop, and out comes your pion. But no, not actually. Have I mentioned that conservation rules all? You have to have momentum conservation. So if this guy is stationary, but you're slamming a moving beam of protons into it, there's momentum in this interaction, which means there has to be momentum after. So you have to give your proton beam much more than 135 MeV to get a 135 MeV particle out. Let's do the math. So let's go to the lab frame where you have a proton beam moving with some velocity v, and it's going to slam into a proton that is stationary. This is our initial condition, and there is momentum here, right? You have the mass of the proton times the velocity of the proton. So imagine you gave this proton that's moving 135 MeV. So that's its kinetic energy. It's going to slam into the stationary proton, and you want all of that kinetic energy to be turned into a pion. So your end result would be two protons and then your pi zero just hanging out. Except this doesn't conserve momentum, right? Because you have momentum here. If all these are stationary, if every bit of that kinetic energy got turned into this mass, you have no momentum. That breaks conservation, which is the biggest rule in the universe. You have to conserve everything all the time. So instead, you need to give this moving proton more energy. It has to have more than 135 MeV. Let's calculate how much that is. Okay, so let's go to the center of mass frame, where your proton is moving this way, and the proton that was stationary is moving this way. Okay? Here, in this situation, momentum is zero because you have an equal velocity going both ways. They cancel out, which means after our momentum can also be zero. So now let's look at conservation of energy. If at the end of this we produce a pion in addition to our 2 protons, this whole situation will have some energy, and it has to be equal to whatever the energy was over here. So when we're looking at our initial energy, we're going to have to account for the relativistic Lorentz factor. And on the right-hand side, after this collision, we're just going to have the rest energies of the particles. So that's going to be 2 mp c squared plus m pi c squared. Let me just plug in gamma. So mp c squared over 1 minus v squared over c squared. And all of these are known values. Like we know the mass of the proton, we know the mass of our pion, we know what C is. What we can do is solve for V in the center of mass frame. And what we get is that that is equal to 0.36 C, which is very fast. But we need the velocity in the lab frame, right? Because remember, we're shooting a beam of protons at stationary protons. So the proton that's moving is going to have 2 times v center of mass. And when you're adding relativistic velocities, you can't just say 0.36 plus 0.36. You have to do the special relativity formula. So let's do that. So v lab is going to be equal to v plus u over 1 plus vu over c squared. Here v and u are equal to 0.36, so when you work this out, you get that v in the lab frame is 0.64 c. So if you want to make a pi zero in your collision, your initial proton has to be traveling at 0.64 c, which is why they make these giant accelerators. You have to get these protons up to relativistic speeds in order to start making stuff. And I think it's easier to think about this in terms of energy. So the energy of that initial proton is going to have to be gamma minus 1. We know this is 938 MeV. So the energy that you're adding into the proton is going to be 280 MeV. What this means is in order to make a particle that has a mass of 140 MeV, you need to put at least 280, probably more than that, 290 MeV into your proton. So this is called the threshold energy. You have to add enough energy to conserve momentum in order to make the mass. So you're making a very tiny particle, you have to put double the amount of energy into your proton in order to get that particle out. This is super inefficient. You have to double the energy you add to the proton beam in order to make these teeny tiny particles. But they're not in it for like efficiency. They're not trying to conserve energy here. They're trying to study those particles. So you have to do that the only way you know how, which is to make them in an accelerator. But what if you want to make antimatter? What if instead you want your proton-proton collision to produce a proton-antiproton pair? You have to put a lot more energy in. Instead of doing the proton plus proton yields proton plus pi zero, you want to do proton plus proton yields proton plus a proton antiproton pair. So plus proton plus p bar. This looks weird, right? Proton plus proton yields 3 proton plus an antiproton, but that's how particle physics works. The math is mathing for us right now. Of course, that means you're going to have to add in the energy of these two masses, plus more, plus the threshold energy to get that out. It's going to be incredibly expensive. So you might say, like, well, if we just have to conserve charge, why can't we do something like this? because now this has a +1 charge, this has a -1 charge, and you're conserving charge, but you also have to conserve baryon number. This is not a baryon. This has a baryon number of -1. If this interaction happened, it would break our rules of conservation, which are immortal and the most important. They're the gods of us. So we can't do this. This would never happen. It breaks all the rules. So even though this would be a lower energy interaction because this particle weighs way less than the proton, you can't make this. This would not work. So you can't do this guy. You have to put in enough energy to make the proton-antiproton pair. So let's calculate the threshold energy for the proton, and we can do the same like lab frame, center of mass frame, Lorentz invariance trick that we used before. So in the center of rest frame, after the interaction, which is like where you have E of proton plus proton plus proton plus antiproton at rest, the energy in that situation is just your proton masses, right? So you have 4 mp c squared. The energy in the lab frame is going to be the energy that's like kinetic energy plus the mass energy, which again, you have to account for relativity. So you get mp c squared over 1 minus your lab velocity over c squared plus mp c squared. So we can set this equal to each other using our little Lorentz thing. Which says that 2 frames should have an equal total conservation of our energy combined with our momentum. So we can do this for the lab frame equals the center of mass frame. In the lab frame, we know that our energy is 4 mp. In the lab frame, we know that the energy is just our 4 protons and there's no momentum. So for E squared on that side, you get 16 mp squared c to the 4th. So I'm gonna call this whole thing mrel to make this just algebra writing down easier, and I'll move to the next step. With okay, so now we're just doing more algebra. We can divide by 2 and then get rid of the mass of the proton, and what we get is this. The total energy of your incoming proton has to be 7 times its mass. The mass of the proton is about 1 GeV, so you have to pump in an additional 6 GeV, giga electron volts, to that proton, slam it into a stationary proton to get your 3 proton plus antiproton interaction. 6 GeV to make a particle that is 1 GeV. That is the threshold energy. It becomes more and more energetically expensive the bigger particle you want to make. Okay, so there was a particle accelerator that was very, very specifically made to be more than 6 GeV. It was like 6.2 GeV. I think it was Berkeley. And that was because they wanted to do this specific interaction. They wanted to make antiprotons. To make one antiproton that is about 1 GeV, you have to put in 6 GeV as the threshold. This is a very inefficient process, and the bigger the thing you want to make, the more energy it takes, which is why people want to build bigger and bigger particle accelerators. They're like, the more energy we could get in, let's make a TeV. The bigger the stuff we could make, the more interesting particle collisions we could do. Think about all the things we could learn from particle physics about cosmology and all the other types of interactions that are happening every day. I feel like the modern person who kind of likes physics has a very negative attitude towards particle physics, which is insane to me, because particle physics is amazing. It's such a successful theory. It's so predictive. You can see these plots of like these particle scatters, and like every single little particle that's coming off has been predicted by the math beforehand. And then they make these big billion-dollar projects, and they're like, oh, see, here it is, we did it. And they can learn even more. And I guess like people put particle physics in the same bucket as string theory, which is just absolutely wild because particle physics is so insanely successful. They will predict a particle, spend 10 years building a thing, and then observe it as soon as they turn it on. It's amazing. Like, of course I understand that someone might say, I don't think it's important that we spend another $100 billion building bigger and bigger particle accelerators. And yeah, I agree with that, right? Like, if you have $100 million, you could fund small projects, and maybe it's not in our best interest to keep building bigger and bigger particle accelerators and spending all this energy to make like these tiny little guys. But if some government somewhere was willing to fund that, I mean, I wouldn't be uninterested in the results. I don't understand. Where is this coming from? Where is this idea that particle physicists are just like lying in their offices? Do you think particle physicists get to keep the $100 million that went towards building the thing? The average salary of a professor is like $90,000. And I mean, that's pretty good in a lot of places, but not if you live in Berkeley. They're not getting rich off this. They're just supremely interested in the results. Like, if we build bigger particle accelerators, which again, I don't think is the best use of our funds, but I mean, I wouldn't be mad if it happened. If we keep building these bigger things, we can learn more about like the fundamental physics that makes everything. And that's interesting. And so I don't understand. Like, I feel like in the comments of my videos, people will just say these horrible things about particle physicists, like they're just making stuff up, when you can literally just sit down and calculate it and then go do the experiment. Where is this coming from? Stop it. Particle physics is cool. I mean, you should be laughing in the comments of whoever is on Facebook posting that particle physics is bad, actually. That's a lame take and it sucks. So CERN and other places also make antimatter. Why do I always talk about CERN? It's fine. CERN has an antimatter factory, and they make antimatter protons, and they make antimatter hydrogen atoms, and I think they made an antimatter helium. I think that was at CERN. I know that has happened. Pretty sure it was at CERN. What happens after that? Well, as I've told you, antimatter annihilates with matter. So if you make an antiproton, you can look at it and it will immediately just find a proton and go and release a bunch of energy. And yeah, so that's what happens to all the antimatter. They make it and it immediately annihilates with a proton. You can trap it. I think the record is that CERN, again, they trapped an antiproton for 57 days in a magnetic field to prevent it from finding any matter to explode with, which is pretty good. But usually they just let them hit the walls of their detector and explode, which I think is kind of interesting. I'd like to talk about another misconception that I specifically had about antimatter when I was like 10 years old. Do you guys remember the movie The Da Vinci Code? I think it was the sequel, not the original. And I also get those movies confused with National Treasure. But he's got like a little like Beats by Dre speaker size thing, and Tom Hanks is holding it and he's like, oh no, there's antimatter in here and he's gonna explode the Vatican or something. And I always thought as a child, when I heard about these experiments, like all you hear is like, if you make antimatter, it makes this big explosion. All this energy is released. And so I was like, oh no, why are they doing this? They're gonna explode the earth. They're gonna make antimatter bullets and I'm gonna die, because I grew up in America. And so when you hear scientists are making antimatter, you're like, oh no, please stop doing that. But like, CERN makes antimatter all day. Well, I mean, whenever it's running. doesn't run that much. But when it's running and it makes antimatter, it makes it all the time. And they just let it hit their walls and it just explodes. And like CERN is still standing. The explosions are not that big. Like one antiproton colliding with one proton, not that much energy, it turns out. I was going to do a comparison from the energy of a proton and an antiproton. Like a proton and an antiproton, if they annihilate completely, it means their total mass has to go to energy, right? And subatomic particles and all that good stuff. So that's like 1900 MeV. And I was going to convert that to a unit of energy we use every day, which is the calorie. But the energy of 1900 MeV is like 10 to the minus 14 calories. So there's no food like that has that amount of calories. It's a very small amount of calories. So you have to understand that one proton colliding with one antiproton is like zero energy. It does nothing to CERN. They just let the antiprotons go and they just hit something, and like the structural integrity of the building is fine, the detectors are fine, nothing happens. It's a very small amount of energy. For some reason as a child I was like, oh God, they're gonna blow up the world. But like their whole production of antiprotons is a very small number, so it's a very small amount of energy. It's just not that much energy. It's totally not a problem. Like if you got shot with a single antiproton, it would find a proton in your body to annihilate and you would not even notice. It's really tiny. Yeah, so this movie is kind of funny on reflection. Also, look at this device. You need these giant magnetic fields to keep these things from annihilating with the container. Like, what's in there? What's in there? How is it doing it? What's going on there? Is there a giant battery somewhere that we can't see? It's kind of fun. Why does a proton annihilate when it hits an antiproton? Why does an electron annihilate when it hits an anti-electron? It's kind of a complicated process, but imagine you have your two boys, your proton and your antiproton, and they have their quantum numbers and their charge and their mass, all of that good stuff. Now you put them together, they're moving towards each other. They have opposite charge, they'll be attracted to each other. But they can overlap, right? They don't have the same quantum numbers because they have opposite charge. So imagine they're holding the same space spatially. Okay, now what you have made is a particle that has a mass of 2 and a charge of 0, right? Because it's 2 proton masses plus 1 charge minus 1 charge, charge of 0. That particle doesn't exist. That, as a state of matter, is incompatible with the standard model. It's incompatible with the universe. It's incompatible with quantum mechanics. And so immediately just energy. It just breaks apart. Einstein's energy mass equivalence, boom, energy. That's what happens. They're attracted to each other because they have opposite charges. They can't exist like this, energy. That's why particles annihilate. So that's probably not a very satisfactory definition for a lot of people watching this video. That's true, but they might want, like, what is the mechanism, you know? And that's fine. I will try to go into a little bit, but you know I don't like doing that. I don't like talking about subatomic physics. It squigs me out, but I'll do it for you. But first, I need to talk about Richard Feynman. Because when you're Googling around the internet about antiparticles, and you're like, why do antiparticles annihilate? You're gonna find like a Reddit thread where someone is referencing Feynman's lectures on physics, and they will say something along the lines of like, antiparticles are just particles moving backwards in time, and they will put up a Feynman diagram that looks like this. And the thing is you can't go back in time. This doesn't make any sense. Like, mathematically, Feynman's description of antimatter matches Dirac's. They give the same results. But as we learned at the very start of this video, sometimes math gives you unphysical answers. Like in this case, where Richard Feynman says that antimatter is just matter moving back in time, because you can't actually move back in time. This is a mathematical formalism that leads you astray with the physical ideas. And I know that this has happened to people because I was Googling around to see how people are describing antimatter, and a lot of the Quora forums and a lot of the Reddit threads and a lot of the Twitter threads are just people being like, it's just an electron moving back in time. There was only one particle the whole time. And I just, no, that's not right. That doesn't make any sense. Mathematically, you can use this to get the answer, but that doesn't mean anything about the physics. Particles, antimatter is not matter moving back in time. You can't move back in time. That makes no physical sense. Are you saying Nobel Prize winning physicist, genius, brilliant physicist is wrong? Maybe he just was like, mathematically this is the same thing, so it's fine. And he did not predict that people in the future would be like, haha, they're going back in time. Alternatively, it could be a joke because Richard Feynman thought that he was very funny. So maybe it's like a joke, like the same way people talk about how there's just one electron, LOL, all the electrons you see are the same electron. Like, no physicist actually thinks that. It's just like a funny thing to say because electrons have to be indistinguishable from each other. So maybe it was a joke. I don't think he actually intended to say that they go back in time. I really think it was just an illustrative example that people have now misconstrued as Richard Feynman saying antimatter goes back in time. I think he was saying to an observer it's indistinguishable, but it's not physically going back in time because that's impossible. But let me give you an example. If you have a gas, like in a box, that's a small box, and you put it in a bigger box, and you remove the walls of the small box, the gas will spread all out. It will move to a more entropic state. So you could say time flows forward with entropy. Okay, so if you have your gas of hydrogen atoms and you put them in your little box, they start all close together and very hot, and then they will move apart and they will spread out to the entire box and they will cool down a little bit. They will get to some steady state of maximum entropy. That's how thermodynamics works. Based on everything we know about anti-hydrogen is that it behaves identically to hydrogen. So if we took the same experiment and we put the anti-hydrogen in a little box inside a bigger box and we removed all the walls, anti-hydrogen behaves with the forces, it behaves with collisions, it behaves with the conservation of momentum just the way hydrogen does. So assuming the box is also made of antimatter so it doesn't just immediately annihilate, that anti-hydrogen would bounce against each other, it would collide, it would move forward in time to a state of maximum entropy. If antiparticles went back in time, they would not do that. They would move to lower entropy, which would be unphysical. We know that antimatter does not move back in time, but also I can't believe I had to say that because it doesn't make any sense in the first place. And I know someone could respond to what I just said and be like, no, antimatter goes back in time, but it follows anti-entropy. And at that point, it's just like, what's the point of that? So it behaves exactly like the physical world, but instead you're just calling it all backwards. It doesn't make any sense and it's just pointlessly confusing. So yeah, it turns out antimatter travels forward in time just like literally everything else because you can't go back in time because that doesn't make any physical sense. Okay. There is a mechanism at work here. People who do this as their jobs are not just saying, oh, they go on top of each other and that can't exist, so boom, right? So it's a very complicated process of what actually happens when a proton hits a proton, but I'm going to try to explain it a little bit for you. You have your proton and your antiproton, and they move together, and these are both composite particles, right? So they're made up of quarks and gluons, and the sea of quarks that is coming in and out of existence all the time that I don't even think I've mentioned yet, it's fine. So two of the quarks will hit each other, a quark and an antiquark, and they will annihilate, okay? They will produce a gluon. What's left is no longer two protons. You have some quarks, an extra gluon, all of that just immediately showers in a very complex process called hadronization. What results from that? like that initial two quarks hitting each other, is energy and a lot of pions mostly. Pions are unstable, so they will decay very, very quickly into electron-anti-electron pairs, photons, that good stuff. You can see in your detector where this happens. You get like quark jets, you get all these curves of the particles leaving, and you can like figure out which particle is which. That's the most I can do for you. This is why we want to build bigger and bigger particle detectors. If you want to learn more about this, you know, stop shitting on particle physics so much. But what if like an anti-electron hits a proton? The anti-electron is not the antiparticle for the proton, so it's not going to make the proton annihilate, right? That only happens when an anti-electron hits an electron. So even something like an antiproton could hit a regular neutron, and they might not annihilate unless the proper two quarks could find each other. But what if you take an antiproton and you slam it into an atomic nucleus, like a big boy, like a uranium or something? What would happen? Because your proton will fly right through whatever electrons are there. It will hit the nucleus, and there's a heck of a lot of protons in there. What if it finds another proton? It will annihilate, but only with one proton, right? But that production of energy will cause the entire nucleus to split apart. And then maybe like secondary fission could happen. You've got nuclear reactions happening. All of a sudden, you have a start process for this runaway nuclear, like, to run your power plant or whatever. It's producing all this energy because you shot one proton into its nucleus. Whoa, you could have this runaway process with energy all from just one antiproton. What if you used all that energy for propulsion? Has anybody thought of this? Could you like make an antimatter engine? Did I just do something? Did we just make this? Oh my, has anyone thought of this? Did I just do something? Oh my God, what if you use this energy for propulsion? Oh my God. Okay, have you guys ever heard of the rocket equation? It talks about how important the mass of your fuel is. Because the more fuel you have to carry, the more fuel you expend carrying that fuel. Do you know what I mean? So we have these big giant booster rockets, and they're carrying this huge volume. And it's just so expensive to get all that up just so you can push the mass up. And the more mass in your payload, you have to add more and more fuel. And the more fuel you have to add, the more fuel you need. It's this terrible problem. Like, the thing about antimatter is that it's really super light compared to like its gas or nuclear fuel component, but it's like 10 billion more times more efficient. Like, that's crazy. That's insanely efficient. Like, that's assuming that, of course, you bust open your antimatter and all of it gets converted to useful energy, which probably wouldn't be the case. But either way, it's still huge. And if you actually want to travel the solar system, you need to be able to accelerate. And the thing that will accelerate you is having fuel. So if your fuel is really light, you can carry more and you can accelerate more. And the thing is that the big boom will make you go fast. So if your fuel is very, very light, you can accelerate more. And the more you accelerate, the faster you go. And that is essential to traveling the long distances of space, because space is huge. That's why antimatter is so very exciting to people. But let's dig a little more into it. Like, how much energy is like a proton-proton collision? I'm going to put up a little flow chart while I talk about this, okay? So a proton-antiproton event is going to give you the amount of energy that is in those two guys, right? 1880 MeV. We know that this is going to make a bunch of pions, and the pi0 pions have a really very, very short lifetime, and they will just immediately turn into gamma rays. And you can't usually use gamma rays for fuel. You just can't do that. So you lose all that energy. You're left with about 40% you've got 1170 MeV split between your plus and minus pions, which are charged, right? So if you were thinking in the future of designing a spaceship, this is where you start designing like magnetic nozzles to push these charged pions out, because all your neutral pions have gone to gamma ray. But if you don't act fast, like on the order of 10 to the minus 8 seconds, those charged pions will then decay into muons and neutrinos. Neutrinos, a lot like photons, they're really small boys. You can't use those as like propulsion. You can't use those to apply a force, to make a thrust. So you're down to 31%, 890-ish MeV in your muons. But you have to act fast, again, because on the order of 10 to the minus 6 seconds, all of those muons are going to turn into neutrinos and electrons and positrons and more neutrinos. And you can't use the neutrinos. Those are gone. You started with 1880 MeV from your proton-proton collision. Now you have some electrons and some positrons, and you're down to 300 MeV, 16% usable energy. So when you're designing something like an antimatter spacecraft or an antimatter rocket, you have to think about how quickly these interactions are going to work. Can you act fast enough to use the charged pions before they start decaying into muons and all your energy goes to neutrinos, which you can't use to do anything, or gamma rays, which you can't use to do anything? Because of our like weight to energy ratio is so huge, billions, literally billions times more than we've ever seen before, it doesn't even matter if the only thing you can use is the last 16% tied up in electrons and positrons. That'll still work for you. This is just one of the things you have to think about when you're designing your antimatter spacecraft or rocket or whatever. I found this report from the government. It's on the internet now. You can just read it. And it was just someone compiling all the current research on antimatter and the outlook for antimatter space travel. And it's super old. Way before I was born. It's from the 80s. Oh my gosh. But I want to share with you some of the designs. How will an antimatter spacecraft work? So the first design for a rocket is a thermal heat exchange rocket. You have a nice little nozzle-shaped rocket that looks like this, and you put in the center of where you're going to collide your protons and antiprotons a big giant block of tungsten. And you're going to smash your protons and antiprotons together, which will release a bunch of energy. We assume that the tungsten will absorb all the photons and all the pions, and it will heat up. And then you can run some hydrogen through that will then be heated by the hot tungsten, and it will push out the nozzle and provide thrust. Cool. You are limited at the temperature because at a certain point, tungsten will melt. And the way you radiate heat, like if you have like a Star Trek ship, for example, and you have something like this that is your method of propulsion instead of like warp drive, the thing is that if you're producing all this heat, you have to make a plan for how you're going to radiate it away. Like, yeah, you have a limit because you can't melt your tungsten or otherwise this thing won't work. But also, what will you do with all that energy, all that heat? You have to get it out of your ship somehow. It's kind of a complicated problem. But also notice that this is just a rocket, right? The rest of the design doesn't really matter. This provides thrust. Presumably you have some sort of magnetic trap that is trapping your antiprotons and preventing them from just exploding whenever you want. And you just push a couple in at a time, they find a proton, they heat up the tungsten, and you have thrust. The next one is pretty similar. It looks like this. It's a hot hydrogen gas concept where you add like a magnetic bottle to your engine. Your proton and your antiproton hit each other. It makes a bunch of neutral pions, which go to gamma rays, which you have to deal with somehow because that's going to heat up your whole ship. But the charged pions will be trapped in this magnetic bottle and they'll kind of be oscillating around, and they will heat up hydrogen that way, and the hydrogen will then provide thrust. Notice these are still using hydrogen. I don't know how they're getting around the weight of the hydrogen, but that's still fine. You need less hydrogen because you have this antimatter fuel. Your fuel still weighs way, way less. I just want to do another one from this 1985 paper. Even though this paper is really, really old, these designs are still kind of how people start to think about antimatter engines and how they would work. we're not any closer to like proof of concept antimatter engine test example than we were 40 years ago when this paper came out. So it's still kind of interesting to talk about all of these ideas, but this one is the last one I'm going to show from that paper, and it's more along the lines of what I thought people were talking about when they talk about antimatter engines. You still have your nozzle, you still have your proton-antiproton colliding, except this time you have a magnetic nozzle to specifically funnel the charged pions out. Like as soon as you make them, you are thrusting them out of the back of your ship, which will provide forward movement for your ship. So this is like a longer term, you don't need the hydrogen as like this buffer between your antimatter and matter and like what the actual thrust is. This is just using the charged pions as the actual thrust. Again, how are they storing the anti-hydrogen? I don't know. Still a very interesting design. This is how I think it would work if you were doing like to Saturn or something, not just like a rocket leaving to low Earth orbit. Just for fun, here's a much more recent example from like 2009. It's an antimatter sail, where you make a sail of like nuclear fissile products like uranium, and you just shoot your antiproton right into it. And just like I was alluding to earlier, you could start a fission reaction with just one antiproton. It would explode a little bit, pushing your ship forward. That's kind of neat. All of these engines will always be accompanied by little charts where they're like, we just need a single gram, just mere grams of anti-hydrogen, and we could go all the way to Proxima Centauri. And I just think that's kind of funny, especially because people have been talking about this for 40 years, because you can add up the total amount of antiprotons that have been made on Earth in like the 40 or 50 years that people have been doing it, and it's like on the order of nanograms. So you're orders and orders of magnitude off. Like as far away as a dollar is from $1 billion, that's how far we are from having just like a gram of antimatter to use as fuel. I recently read this article about antimatter engines, and it talks about how all of the antimatter produced on Earth in a year is enough to power a single like small light bulb for like 3 seconds. All the antimatter produced on Earth ever could like boil a pot of water. That's how little we've made. Like if you go to the Wikipedia page, CERN will be like, we made, let me find it actually, Angela. In November 2010, the Alpha Collaboration announced that they had trapped 38 anti-hydrogen atoms for 1/6 of a second, the first confinement of neutral antimatter. In June 2011, they trapped 309 anti-hydrogen atoms, up to 3 simultaneously for up to 1,000 seconds. And here's the thing, if you say that you trapped 309, I assume you trapped 309 simultaneously, but really they just had 3 at a time. And for the space thing to work, you need a gram, which doesn't seem like a lot, but the difference in 3 hydrogen atoms and a gram of hydrogen is Avogadro's number, which is a huge number. So it's been 40 years. We just can't make this stuff in the quantities required. We can't store the stuff in the quantities required. Like, yes, this is an interesting idea and it would work. Like, theoretically, this would definitely work, but we have no way to do it. How do you do it? You can't make it. You can't store it. How do you do it? I also think it's really interesting how when people talk about antimatter engines, they talk about how like fuel efficient and like it's going to be so much cheaper. But do you remember the calculation we did earlier where it takes 6 GeV to make one GeV antiproton? That's way more. Like, yeah, in space we're using way less energy, but we're heating up the Earth. We're using like the power grid. I mean, I'm pretty sure CERN has a bunch of solar panels and stuff, and if you go to their website, they're like energy friendly. Look at the butterfly habitats, the orchids, but like they're also in the power grid, and they are using all this power to make these teeny tiny boys. And if it was possible to make a gram of antimatter, it would be very, very expensive. We would be using fossil fuels to do that. It's not efficient at all. It's incredibly inefficient. It could be Some might say the most inefficient thing I've ever heard of, the most expensive material to ever exist. Here's the calculation. Here it is. I don't have to take you through it. But it's like $6 trillion per milligram. So if you need a gram, I'm just Googling what's after trillion. Quintillion. It's like $6 quintillion to make a gram. That's a lot. That's a lot. No, this isn't happening. I don't know what to tell you. There was a little article from 20 years ago where they were calculating, like, if we could just speed up our production, and yeah, it's like quintillions of dollars. And this is from the year 2000. So like, just put inflation on that. Like, it's not efficient if you have to make it and spend all this money and heat up the planet from all the energy you're using just to make a gram. Like, that's one trip. And guys, when they say, oh, you just need 1 gram and we could go to Proxima Centauri, they're not talking about we make a Star Trek ship and we put 30 families on there and tell them it's going to take 55 years and they're going to go to another star system, even though we can't tell if there's like livable planets there or not. They're talking about we can make a probe that weighs 10 or 20 kilograms, and that would take 50 years to get to the nearest star, and hopefully we could get the data back. And that's what we're spending the trillions of dollars on if we make the thing. Anyway, people do talk about storing it, although the people who talk about the engines never talk about the storing it. But hydrogen, anti-hydrogen, like hydrogen, has like a magnetic dipole moment, and so you can just make a little magnetic trap. Not little like on the Da Vinci Code, but like you could just make one. Here are some designs, and there are some ones where they have like anti-hydrogen balls and like these like bumper style things. That's interesting too. So like all of these problems, engineering wise, seem like totally feasible in my opinion, but I'm not an engineer. What do I know? But I am a physicist, and making a gram of antiprotons, no, that's not happening. But you can say this is how they could work. It's just you don't have the fuel. You can't make the fuel. That's the issue. I don't know if I've ever gotten a chance to talk about this on my channel, but when I think about space travel, what always like bugs me is deceleration. Like, yeah, if you had antimatter fuel, like a lot of it, like you magically made it and you magically made the ship and you're magically storing it and it's all magically working, and you can speed up to, I don't know, like 0.3 C, which would be insane. That would never happen. But imagine you could. Like, it would take like a decade to speed up that much. And then like, oh, you can go your 5 light years in like a decade. But if it took you a decade to speed up, it will take you a decade to slow down, because you basically just have to turn your rockets on and point them the other way to slow your ship down. You can't approach a planet at 0.3 C. That would bust everything apart. It's like you're driving a car. You can speed up to like 60 miles an hour pretty quickly, and you can also slow down to 0 miles an hour pretty quickly, right? You just slam on your brakes. But in space, there's no road. There's no like friction. There are no particles to slow you down. You have to just turn your rocket around. And if it took you 10 years to go that fast, it will take you 10 years to go that slow. And I just can't imagine people signing up for like 10 years of speeding up, 10 years of traveling, 10 years of slowing down. Can you imagine you start like your slow descent and it's gonna take a decade? No one ever talks about slowing down, and people will just be like, oh, you could just have sails like one of those race cars. And it's like, there's no air in space. There's no stuff in space. Like, the thing that slows you down is friction, which is just the electromagnetic force, which requires like particles, and space is pretty empty. You know those probes that like NASA and other governments and other space organizations, I'm sorry, I'm an American, they'll like send them through the asteroid belt. They don't even plan for that. They don't even have to think about, oh, we got to avoid all the asteroids, because like space is just empty. Even in spaces that we think of like as full, they're empty. There's nothing there to stop you. You're going to be slowing down for decades. That's terrible. That's a nightmare. No, thank you. Maybe you could have a little pod and the ship could like throw it backwards and it could slow you down that way. I wonder if that would work. Did I just do something? So in September of 2023, I saw this really cool article about this really cool experiment where they measured the gravitational effects on the motion of antimatter atoms. And I thought, oh my God, they did it. That's amazing. How did they do that? And then I was like, what a thing to make a content about. But then I got distracted by like bad science news. And then I was like, well, if I'm gonna make a video about an antimatter experiment, I should talk briefly about antimatter. So if you need to know about antimatter, watch this one first. But briefly, antimatter and antimatter hydrogen, which is what we're going to be looking at, is made up of an antiproton, which is the same mass as a proton inside of a regular hydrogen, but it has the opposite charge, and it's surrounded by an anti-electron, sometimes called a positron, that is the same mass as a regular electron, but it has a positive charge. So this is what a regular old hydrogen looks like, and this is what an anti-hydrogen looks like. And the thing about antimatter and matter is that when you make particles, they are made in pairs like that, right? So you'll make an electron, but you'll also make a positron every single time. But when we look around the universe, the big question is like, okay, but everything's made of matter. Like this meat sack sitting in front of the camera, made of matter. The antimatter is not around. So open question. So that's one of the reasons we want to study antimatter, so we can try to explain like what happened early in the universe that led to where we are now, where it seems like matter has won and it is just dominated over the antimatter. Where did that go? We have to study the antimatter to answer that question. One of the ways we do that is by learning about its basic properties, like how it interacts with gravity. So we're back around. So you might have seen this paper and said, why would they measure that? Of course antimatter falls down. What a silly thing to measure. Of course gravity works the same for matter and antimatter. Of course it does. Why would you spend, presumably conservatively, hundreds of millions of dollars at CERN measuring the fact that antimatter falls down? Of course it falls down. And I would like to answer that question of why would you do this with 3 very specific reasons from 3 different experiments. It's a framing of a video. So the first reason why you would do this, why would you measure antimatter falling down? Of course it falls down, is because like you kind of just have to check, right? What if it didn't? You have to check. That's my favorite kind of experiment. Like, is this gonna happen the way we expect it? Yep, it did. So the year is 1957. They're doing a conference, with physicists about particle physics and all the stuff, like your post-World War II style of physics. And Bill Fairbanks, American physicist, was there, and I think he was just a student at the time. And in the session on antimatter, the session chair, Bryce DeWitt, says this: nothing is known about the gravitational acceleration of antimatter. So this was just a statement of fact. At the time, in 1957, no one had measured how the very newly discovered antimatter interacted with gravity. And this just kind of wiggled its way into Bill Fairbanks' head. And he just kind of sat on that. And then years later, in 1968, he's a professor at Stanford. And his student Whitburn and him decide, let's test this. So they develop an experiment to measure how gravity affects the motion of electrons, with the ultimate goal of then testing positrons and comparing the results. Do you get the same value for gravitational acceleration for an electron and a positron? You should, if it only depends on mass, which we expect it to based on what we know about gravity. So they developed this free fall apparatus where they kind of shoot electrons up and they want them to fall down. And they can put some like fields on it to try and supplement gravity in one way or the other, because of course electrons have charge. They will be strongly affected by any fields much, much more than they would gravity. So the idea is like, oh, we could do an artificial gravity type situation by putting an electric field around this and maybe comparing it with different values of the field, and maybe that would be a good proxy for measuring gravity, because gravity is orders and orders and orders and orders of magnitude weaker than the electromagnetic force. So if you're going to measure something like how a charged particle interacts with gravity, you need to have complete, accurate knowledge of every single electromagnetic field that particle is also experiencing. Otherwise, you're not going to be able to pull the gravity out, because the gravity is just so much, much more weaker. And it turns out that this experiment is just impossible. Like, you can't do it, especially in 1958. Like, yeah, you can make a beam of electrons, you can try to remove as many electromagnetic fields as you can, but environmental effects will just overwhelm the numbers, and you cannot pull out gravity's contribution to that motion, because that contribution is so tiny. So the goal of measuring the gravitational effect on electrons and then comparing it to positrons never happened, because they just couldn't do the experiment. Of course they got results, but they weren't confident that they had actually measured the value. So they published this Nature paper in 1968, and they're like, great idea, we just can't do it yet. And Bill Fairbanks kind of continues this work. He goes on talking about like why it's important to study the gravitational effects on antimatter particles. Like, what could that tell us? And of course, we don't know anything about it until we can measure it. And that's why we do the physics, right? To learn things. That's my favorite reason to do anything. Like, are you sure it's going to happen the way you think it's going to happen? The second reason, which will lead to our second experiment on like why you want to study what happens when antimatter interacts with gravity, of course it falls down, of course it does, is because we don't really understand gravity. I would put an asterisk on that. We have this wonderful theory of gravity called general relativity, and it makes all these predictions, and it's always right, and we love to see it. However, on the smallest scales, like the Planck scale, we expect that our wonderful theory of gravity does not, well, I guess we don't expect it. We know that our wonderful theory of gravity, general relativity, will not match the results from our other wonderful theory, like standard model physics, standard model cosmology. Like, you have your quantum mechanics and your QCD and all of this stuff that works really, really well. They just don't match on the Planck scale. And people don't like this. It's very upsetting for some people. And so they develop ideas like quantum gravity, which is just string theory. In order to understand gravity, we need to do experiments with it. We need to test what we think will happen in order to ensure that that's what will happen, or maybe something will be different. Maybe we will do a test on gravity one day and we get the unexpected answer, and then that will be a clue on how we can solve this big problem. So one of the things they test is the weak equivalence principle, which is a requirement of general relativity, which says that inertial mass and gravitational mass are the same mass. There's just one type of mass and they have to be the same, which means that every body will experience gravity the same way. Been known since Galileo, if things are in free fall and they are dropped at the same time, they will fall at the same rate and they will land at the same time. Their inertial mass is identical to their gravitational mass, but we have to test it. So we can test the weak equivalence principle by ensuring that antimatter, such as an antiproton, will fall in exactly the same way that a proton would. And any difference in that measurement is a clue on how we can fix gravity at the Planck scale. We really have a handle on it in every other context, guys. I'm a general relativity stan. Deal with it. We don't need quantum gravity. Get out of here with that. So push forward in time to the 1990s. We're getting a lot better at making antimatter, and the dream of having an antiproton beam is right there for us to grab. And we're like, okay, what if we take Fairbanks's idea of, just dropping electrons, and instead we drop protons and antiprotons because those boys are 2,000 times more massive than electrons and positrons. The more mass you have, the easier it should be to measure the gravitational effect, right? 2,000 times larger. This is it. We're gonna do it. So I'm gonna read to you from a little conference proceedings that I found from 1990, and it's about an antimatter gravity project that was going to take place at Lear, or the Lear facility, which is at CERN. And they cite heavily Fairbanks' idea. What they plan to do is build a device that will shoot antiprotons up. They can put a thin film of some material they don't describe, which the antiprotons will shoot through and will slow them down. And they will slow down, they will rise up, and then hopefully you can observe them falling back down. The trouble is finding a gravity-dominant space from which to launch. Like, oh, it's been 20 years, man. Yeah, that's the problem. There's electromagnetic fields everywhere. Where is your gravity-dominant field? What are you doing there? How are you solving that problem? It's the same thing. Because the thing is, this is impossible. You can't do this with a charged particle. There's just too many fields, man. Gravity is so weak. You can't do it. You can't do it with a charged particle. But they're very confident. They're super confident in this conference proceedings. And they frame this experiment, which there's this whole thing with like funding and like prestige and how you present your results. Like they're doing the exact same experiment that Fairbanks is doing. Fairbanks was framing it as like, this is important to test. Isn't it interesting? No one knows what antimatter does with gravity. They're framing it as, we don't understand gravity. This will be the first ever test of the weak equivalence principle. They're going to do it. They're going to get an antiproton beam. The antiproton is 2,000 more times massive. They've solved the problem. I feel like I've already hinted that. Of course, this does not happen. But I love how they end the paper. After measuring G for protons and negative hydrogen ions at Los Alamos, the experiment will be moved to Lear in order to measure the gravitational acceleration of antiprotons and thereby perform the first test ever of the weak equivalent principle for antimatter. No, they didn't. This didn't happen. This like lost funding and it just never happened. They probably realized that you can't do it with charged particles, and they started working on the one that actually worked, which is the one I'm going to talk about next. I do think it's interesting how the framing of this problem has changed, because in the 80s and 90s, it was all like gravity. We don't understand gravity. What's going on with gravity? In this experiment, which is called Alpha G, I feel like they start talking a lot more about we need to understand antimatter. Because of course there's the whole baryogenesis problem. Like we know that when you make an antiproton, you have to make a proton. So where are all the antiprotons? This is a huge open question for cosmology and like what we know about how the universe works. And yeah, they talk about the weak equivalence principle, but it seems much more focused on we need to learn the properties of antimatter in order to understand antimatter. Because what if antimatter falls down, but it's like a little bit different? Like gravity affects antimatter in just like a slightly different way, or maybe just being present in a matter space, antimatter behaves differently. And what can we learn about antimatter? That's the framing of this. This is the third experiment, the big one. Why would anybody measure the gravitational effect on antimatter? Because we don't know anything about antimatter, and it's important. Because we don't know what happened to all the antimatter. Where did it go? And I would love to walk you through this experiment because it's so stinking cool. Okay, so I'm just going to be reading from the Nature paper. I will link it below, of course. So the idea is not much different from Fairbanks' original idea. However, instead of using a charged antimatter particle, they're using a atom, a anti-hydrogen. So the charge should be zero, should nearly zero. You can still trap it with magnetic fields because of like quantum mechanical spin, but it's fine. Electromagnetic fields won't play as big a role in this because it's an atom. It's not an ion. Great. That's how you got to do it. That's how it has to be done. So they have this vertical trap. They pile up they're anti-hydrogen. They have like a anti-proton beam, and it shoots like a bunch of anti-protons in like a plasma, and then they shoot in your anti-electrons also in a plasma, and then from that you get a couple hundred anti-hydrogen, and you can store them. And so you have this little canister of anti-hydrogen, and they release the top and bottom walls of the magnetic trap, and they observe what happens. And what should happen is that most of those anti-hydrogen should fall down. Like, they're in a canister, you remove the floor, it should fall down. Of course, because this is like a plasma and those things are interacting with each other, you would expect some of them to have a velocity that would allow them to go up. But most of them, if antimatter interacts with gravity the way we expect it to, of course it falls down. Most of them will fall down. What happens when these guys escape is that they just hit the walls of the apparatus and they immediately annihilate, which sends a signal to their detector. And I mentioned this in my other antimatter video, but I still think it's hilarious that as a child I was terrified of people making antimatter because, oh my gosh, it annihilates and it's going to destroy everything in its path, when they literally just let it annihilate in the cage and it does nothing to the device. It's totally fine. It's so little energy. You'll never have an antimatter engine. There's so little energy there. You have to make so much. It takes them all that time to make like 200. Anyway, so they drop the walls. Some of them go up, some of them go down. Where they hit the detector and annihilate allows them to determine if that anti-hydrogen went up or if it went down, and they can just start doing statistics on how many did what. It's really interesting to me that they have to cycle through to get a big enough pile of anti-hydrogen. Like, they're making like 10 to the 6 antiprotons, and they're shooting in a similar amount of anti-electrons, and through each little collision of those two plasmas, they get a few anti-hydrogen. So those anti-hydrogen hang out in the trap, and then they kind of run again, and they pile them up. They call it stacking until they get a couple hundred, which is such a teeny tiny amount of anti-hydrogen. This device is so small. I think they have the numbers. 4.4 centimeters in diameter, 25.6 centimeters in height. That's a little teeny tiny boy where they have 100 or so anti-hydrogen. I like this line too. They say, we typically accumulated anti-atoms for 50 stacks in roughly 4 hours, resulting in about 100 atoms trapped. So if you compare 100 atoms to Avogadro's number, it's like 0 atoms. So like, we're never gonna have an antimatter engine, guys, but it's still really, really cool. They've run numerical simulations where they expect that if they did this same experiment for hydrogen, regular standard hydrogen, which we know how it interacts with gravity, 20% of them would go up and 80% would fall down. So if anti-hydrogen behaves the same way as we expect it to, we should see those same numbers. 20% should escape to the top, most of them, 80%, should fall down. And they do this really cool trick where, in addition to just running like standard gravity, they can put in magnetic fields that will apply an upward or a downward force on the anti-hydrogen. So they're like, okay, if in a normal situation 1g is pointing down, we can make a magnetic field that will apply a force that will push these particles up by 1g. In that case, you would expect half to go up and half to go down. And then they're like, okay, well, gravity is 1g pushing down. What if we put 10g pushing up? We like artificially do that with a magnetic field. Then you would expect all of them to go up, right? And they can do the same thing by applying a downward force and being like, okay, now these anti-hydrogen are experiencing 5Gs of force. All of them must come down. And they can do that to kind of calibrate their machine, but also get really good number statistics on what's happening. And they have this beautiful little plot where they've done exactly that. So they have escape histograms where down is to the left and up is to the right. And they've increased in values of g, where like 1g is what we experience with gravity. And at 1g, they see just what they expected, like 80% fall down. You can see as they increase gravity by adding in that field to apply a force, more and more of the particles start coming out of the down end, just like you would expect. And when they increase it the other way, more and more of the particles start going out of the up end, just as you would expect. You're starting to think like, hey, anti-hydrogen does interact with gravity just like we expect it would. Isn't that really cool? Each of these runs with the different levels of gravity were done with like 300, and the paper goes into a lot of detail on how they determined what was what and their methods and their statistics, and it's a really easy read. I recommend it. I'm not going to go through all of it right now. So here's that same histogram, but as a table, and you can see what's happening, right? Like, as they're changing the direction of gravity, the numbers that go up and down change with it, exactly as you would expect. What a nice little result. Of course, antimatter falls down. And the big plot of the paper is figure 5, where they're comparing their experimental data to what would happen if the anti-atoms didn't experience gravity, which is the middle line, to what would happen if they experienced gravity, just like regular atoms do, and then if they experienced anti-gravity. And you can see that the data fits really nicely with they experience gravity. Let me read it to you. Qualitatively, the experimental data in figure 5 exhibit the behavior characteristic of gravitational attraction between antihydrogen and the Earth. At a bias of about plus 3g or minus 3g, the anti-atoms exit predominantly at the bottom or the top of the trap, as the magnetic imbalance is significantly larger than g. The fraction exiting through the bottom increases monotonically as the bias increases from minus 3g to 3g. The balance point is close to minus 1g, as naively expected from the simplified one-dimensional argument presented above. They did it! Yay, go CERN! So now let me read you their conclusions. We have searched for evidence of the effect of gravity on the motion of particles of neutral antimatter. The best fit of our measurement yields a value of 0.75 plus or minus 0.13, which is statistical and systematic errors, plus or minus 0.16, which is simulation errors of G. So I just want to make a little comparison for what we know about hydrogen and then what we know about the antihydrogen now. And these numbers, even though the error bars on one is a lot bigger, are the same number. So antimatter falls down. Of course it does. But now there's statistics, and they go into a lot of detail on reducing these error bars. They talk about getting slower antihydrogen, which will make it easier to measure, which will also lower errors. They talk about changing the dimensions of the trap, all of this stuff to really nail down these error bars and get a better number. But this is a really exciting, like, first pass results. The conclusion also says, consequently, we can rule out the existence of repulsive gravity of magnitude 1g between the Earth and antimatter. The results are thus far in conformity with the predictions of general relativity. Hell yeah! General relativity, you've never been wrong, man. Keep getting it. Our results do not support cosmological models relying on repulsive matter, antimatter gravitation. So there is a cosmological model that suggests that if antimatter follows anti-gravity, like repulsive gravity instead of gravity, it could explain all of the dark energy and all of the dark matter. And it's kind of a fringe theory, but they say they've ruled that out. I think that's what they're referring to here. They also talk about how in the future, when they do try to like lower the statistical error in order to get a much stronger number, they are going to do it so that they have a stringent test of the weak equivalence principle. So it's kind of also back to gravity. But I just love this experiment. I love the simple, I mean, I know this isn't simple, but it's such a simple idea. This is essentially the same experiment that Fairbanks wanted to do in 1968. He just didn't have the antimatter. It's hard to make. It's hard to get to a neutral antimatter. And here we are in 2023, and they did it. They did it. Of course antimatter falls down. Of course it does. Listen, CERN, I know that you're some of the best experimental physicists in the world, and I'm just a theorist, and this is not even my field of expertise, but if I had one critique, I wish you would have done this experiment with hydrogen. Like, just to compare. Like, you've done it with anti-hydrogen, and you're comparing it to simulations, but you have the device. Like, surely CERN has a beam of protons and a beam of electrons, and they could just do the exact same experiment. And we get a nice little, like, see, it's the same. See, of course they fall at the same time. That would be cool. I love how they end this paper. Formerly the subject of countless thought experiments and indirect inferences, the motion of antimatter in the gravitational field of the Earth finally has a sound and promising experimental foothold. Nice. What a nice experiment. I love this paper. I love this result. General relativity wins again. We did it, boys. So let's talk about why antimatter and anti-gravity are always talked about at the same time, because I don't really understand that either. Like, here's the thing. You have the standard model of particles, like your protons, your neutrons, all that good stuff. And as I talked about in that other video, in 1928, Dirac has this theoretical result where he's like, you guys, there could be antimatter. And then 4 years later, it's like, oh, here's the antimatter. So you have the standard model of particles, and then you have the antimatter particles with a little bar, right? Great. When people think about anti-gravity, which they mean, like, instead of attractive forces, they have repulsive forces, I don't understand why they expect antimatter to be the one that follows anti-gravity. I mean, what indication do we have that it would be? Of course, because gravity is not in the standard model, but whatever. But I always imagined it when I heard about anti-gravity, like before I studied physics and realized that, of course, there's no anti-gravity, whatever. I always imagined it as like, okay, you have your standard model particles, you have your antimatter particles, you have your standard model particles that are anti-gravity. So like, imagine you have a proton, you have an antiproton, you have an anti-gravity proton, like you could have a little dot on top or something. No, the dots take it. Do like a little triangle on top for anti-gravity. Like this time the gravity goes up, so it's a triangle pointing up. And then you would have an antiproton with a bar, but also a triangle, because like I imagined, like if you have a graviton or if you have some sort of gravity charge, proton and antiproton have a +1 because they interact with gravity the normal way. And then these guys would have a -1. Why did people always put antimatter in the anti-gravity pile? I read all these papers. All I saw was these really hideous, annoying debates about, like, you think you've proved anti-gravity isn't real, but all you've proven is that an anti-apple will fall to an anti-earth, and it was lame and boring. So I don't know. But let me tell you about the first man to disprove anti-gravity, and like we couldn't just let him have it. We have to do this all the time. It's Maxwell. Have you ever read Maxwell's A Dynamical Theory of the Electromagnetic Force paper? It's very long, but I feel like I've mentioned that people should read it before. There's a little section on gravity, which again, I'm just going to read aloud to you. I'm so sorry. After tracing the action of the surrounding medium, both the magnetic and the electric attractions and repulsions, and finding them to depend on the inverse square of the distance, we are naturally led to inquire whether the attraction of gravitation, which follows the same law of distance, is not also traceable to the action of the surrounding medium. Gravitation differs from magnetism and electricity in this, that the bodies concerned are all of the same kind, instead of being opposite signs like magnetic poles and electrified bodies, and that the force between these bodies is an attraction and not a repulsion, as in the case between the electric and magnetic bodies. So he's just saying that gravity looks a lot like the electromagnetic force, but we don't have negative gravity. We don't have that. Why is that? The lines of gravitating force near two dense bodies are exactly of the same form as the lines of magnetic force near two poles of the same name. But whereas the poles are repelled, the bodies are attracted. I'm not going to read the math. I hate reading math. That if R is the resultant gravitating force and R prime is the resulting magnetic force at corresponding parts of the field, the intrinsic energy of the field of gravitation must therefore be less wherever there is a resulting gravitational force. What this means, and remember, this is before general relativity. This is Maxwell. No one gives Maxwell enough credit. Oh my God. I mean, if you haven't read this before, like, sit down. I'm going to read it to you now. As energy is essentially positive, it is impossible for any part of space to have negative intrinsic energy. Hence, those parts of space in which there is no resultant force, such as the points of equilibrium in the space between the different bodies of a system and within the substance of each body, must have an intrinsic energy per unit volume greater than, where R is the greatest possible value of intensity of gravitating force in any part of the universe. Oh my God. This is before Einstein, guys. This is before This is before general relativity. Okay. The assumption, therefore, that gravitation arises from the action of surrounding medium in the way pointed out leads to the conclusion that every part of the medium possesses, when undisturbed, an enormous intrinsic energy, and that the presence of dense bodies influences the medium so as to diminish this energy wherever there is a resultant attraction. Guys, he said that gravity is trapped in space. He said it. I've said this in a video before, but Maxwell died when he was 48, which is so young. And this is what he was doing just before. He would have done it. He was so close. But listen to the last sentence. As I am unable to understand in what way a medium can possess such properties, I cannot go any further in this direction in searching for the cause of gravitation. What a way to end that. Just like, here, let me just point out how general relativity works, and then, like, I don't know. What do you think, guys? What do you think? And Einstein could think. Einstein standing on the shoulders of Maxwell. And then he just goes on to, like, okay, now here's my theory about condensers. Brilliant. So Maxwell says that you can't have repulsive gravity. That doesn't make sense because of energy conservation. And people have been debating this for years and years and years, and there's some version of quantum gravity where, like, actually it doesn't break CPTs, or, like, it's fine, strings, and okay. But the reason people keep thinking about anti-gravity and antimatter at the same time, I do think, is because of Dirac. Dirac did that thing where he was like, guys, antimatter isn't excluded. We can have a proton with a negative charge. It's right there in the math. And then someone found those things, right? So if you do a similar thing that I talked about in this video with general relativity, you can come to the conclusion that's like, general relativity doesn't say you can't have repulsive gravity. It could be there. It could be. Maybe it's the antimatter. It's the same thing, kind of, right? The huge difference is that Dirac suggested, hey, maybe antiparticles, it's not allowed. And then we found the antiparticles. Like, maybe we could have repulsive gravity, maybe it's fine. But the thing is, we haven't done the second part. Like, yeah, it's allowed in the math, but you need an experimental verification. You need to find the anti-gravity. You need to observe it. You need to touch it and poke it with a stick. And we haven't done that. So there's no anti-gravity. It's just a little thought experiment that has not yet fruited anything. So why do people keep talking about it? Well, here's my idea. Here's my theory. Here's my tinfoil hat. So in the 50s, 60s, 70s, like, you have this fabulous time where you're like, oh, the weak force, oh, the electro weak force, oh my gosh, renormalization, oh my gosh, you can't renormalize gravity, it's a problem, what about anti-gravity? And then, like, sci-fi authors started putting, like, anti-gravity devices, like, oh, what if you had an anti-gravity engine? And it's in Star Trek and Star Wars and stuff. And that kind of got seeded in people's brains as, like, a thing that was possible, even, like, no, it doesn't even make sense. And then you have, like, crackpot theories about anti-gravity, and there's a whole bunch of conspiracy theories about, like, don't you know this physicist in 1954 discovered anti-gravity and she got secreted away by the government, and there's, like, another guy from a different country and the same thing happened. And it's just like, if it was so easy to find anti-gravity, people would do it all the time. Michio Kaku would have done it in his garage when he was a teenager. Like, no, it doesn't make any sense. What would that even look like? Like, if everything was repulsed by other masses, then everything would just be isotropically spread apart. It doesn't make sense. You would never find. It's fine. Because the thing is that, of course, antimatter falls down. Everyone expected it to fall down. Ask any physicist. So why? Why, when I'm so excited to learn about this result and I go to, like, the news, are, I want to say, a generous 50% are like, they did it, antimatter falls down, and the other 50% are like, scientists baffled, scientists schooled again. And it's just like, no, we knew it was gonna fall down. Of course it falls down. My favorite, and I mean least favorite, is this one from some website called Futurism, where they say scientists disappointed to find that antimatter falls when you drop it. They're disappointed. What? They just did an amazing thing. They just did an amazing thing that was like a little seed of an idea in someone's brain in 1957, and then they started doing the experiment in 1968, and now it is 2023, and they did the thing, and it's amazing. And you think they're disappointed? Who wrote that headline? What the fuck? If you actually read this article, there are lots of quotes. Like, he says, the bummer news didn't exactly come as a surprise. And there's a quote from a physicist at Berkeley, and he says, if you walk down the halls of this department and ask the physicists, they would all say this result is not the least bit surprising. Yeah, of course antimatter falls down. Why would they be disappointed? It doesn't make any sense. This article is just like, if antimatter didn't succumb to the effects of gravity, we could theoretically create a perpetual motion machine. Oh yeah? Well, if friction didn't exist, we could also make a perpetual motion machine. If magic existed, we could make a perpetual... What are you talking about? What? You think the people who spent the last 30 years getting funding and setting up an experiment and running tests and training students are like, oh man, we can't make a perpetual motion machine now. All we did is this fundamental measurement. Oh man, I'm so disappointed. I hate it. I was trying to think of why someone would be disappointed with this. I'm not an experimentalist, I'm a theorist, and I do simulations, and like the standard way you approach it is like, I'm supposed to know the theory. I program the computer to do the thing I want it to do. I should know what the answer will be, right? Like, I shouldn't expect the results. And if I don't know, I run a simulation and I open up the snapshot files and I'm looking at it and it looks totally different than what I expected. My brain doesn't go, oh yay, new physics. I trust what the computer says to me. No, my brain goes, man, I did something wrong because this is not what I expected at all. This is a problem, right? So I just imagine all the grad students who were working on this experiment and they get the data back and they're like, oh, thank God it does exactly what we thought, so we don't have to spend 2 more years trying to figure out all the things we messed up with the statistics or whatever. No one is disappointed with this result. This is amazing. It's kind of shitty. It's kind of shitty to take all this work and be like, oh man, sorry scientist, antimatter falls down. Of course it does. Okay, so in this paper, they mentioned something I've never heard of, the Microscope mission to test the equivalence principle, but in space. And I've never heard of that. And I thought that just was really cool. So I want to read you the abstract. The Microscope mission was designed to test the weak equivalence principle, stating the equality between the inertial and gravitational masses. Its experimental test consisted of comparing the accelerations undergone by 2 collocated test masses of different compositions as they orbited Earth by measuring the electrostatic forces required to keep them in equilibrium. This was done with ultrasensitive differential electrostatic accelerometers on board a drag-free satellite. Doesn't that sound amazing? Oh my god, experimental physicists are so cool. The mission lasted 2.5 years, accumulating 5 months worth of science freefall data, 2/3 with a pair of test masses of different compositions, titanium and platinum alloys, and the last third with a reference pair of test masses of the same composition, platinum. They summarize the results, and they find that the weak equivalence principle holds. General relativity did it again, boys.